Hello everyone, my name is Olivier Klein, and today we will look at how AWS software development kits, or SDKs in short, can be used to build elastic, highly available and cost-effective mobile apps that are directly connected to the AWS cloud without any service in between. In addition, we will learn how AWS Mobile Hub can further simplify building, monitoring and testing a mobile app. So let's get started. If we are to build a mobile app, it often boils down to a variety of common functionalities. We want to authenticate and manage your user's identity and allow them to use your app on multiple devices while preferences and data are constantly synced. All cloud resources must be securely accessed by authorizing only the minimum necessary access. Testing our app is key of good quality control. So we also want to test across multiple devices and different versions of operating systems. Straight from day one, we also want to track user engagement and understand how our app is being used. All whilst we are able to provide functionalities in the backend, allow users' content to be stored and delivered effectively, send push notifications, and record all user events in real time. This will then translate into the following AWS services: Amazon Cognito, AWS IAM, Amazon Device Farm, Mobile Analytics, Lambda, S3 and CloudFront, mobile push notifications of SNS, DynamoDB, and Kinesis. Now, let's walk through each one of them to get a better understanding of what those services are and how we could use them. We will show a few code examples for Android phones, but all of these services can be accessed via AWS SDKs, which are published for a growing amount of the most popular programming languages. All right, let's get started and build an app. Let's start off with Amazon Cognito to authenticate users and synchronize their content. Amazon Cognito allows us to uniquely identify users across multiple of their devices. This can be authenticated or anonymous. If it's authenticated, we provide the flexibility to use third-party authentication providers such as Facebook, Twitter, Google, Amazon, or any OpenID provider. You can even use your own login mechanisms if you currently have one. Amazon Cognito will now create a unique user identity to track your user, but it will also issue temporary credentials to the application to securely access other AWS services according to our security best practices. Lastly, Amazon Cognito also creates a local data store on the device, where you can store information such as user preferences in key value pairs, and these information will automatically be synced to the AWS cloud and all the other devices the user is using now or even in the future. Initializing the Cognito client is easy. With one line of code, we will call the Cognito caching credentials provider, which will handle the rest for us. We only need to provide it a few more parameters, such as the region we are running in, or our account ID and some of the IAM roles we are using. We will look at IAM roles in more details in just a bit. Please also take note of the last line of code here. It demonstrates how we can now access other AWS services, here it would be DynamoDB, fully authenticated according to our security best practices without hard-coding any credentials. Now, I also mentioned the local data store that Cognito provides and which it syncs back to the cloud and other devices. Using this is as simple as initializing a Cognito Sync Manager class and creating or opening up an existing data set. With simple put, get, or remove operations, we are now able to store information locally on the device. The last line of code tells Cognito to synchronize all these information to the cloud and subsequently to all other devices of that user. All right, now we successfully authenticated our users and provided them with temporary credentials to access AWS directly from their device. Now let's have a look at how we authorize access. Identity and Access Management, or IAM in short, allows to control access to your AWS resources. You can create users, groups, or roles to whom you grant or prohibit access to AWS resources via IAM policies. Those IAM policies allow for fine-grained access control to define exactly who can do what and from where. If you have an existing user directory in place, such as a Microsoft Active Directory or LDAP, you can also federate these users back into your AWS environment via IAM roles. Lastly, we also provide the capabilities to easily add multi-factor authentications using hardware tokens or smartphone apps. Now let's have a look at how permissions work with IAM. Here you see two IAM policy statements. This policy is defined as JSON document and permits to specify which resources users are allowed to access and which one they are explicitly denied access. In the following example, we created two statements. The first one allows a user with the listed IAM policy to perform all operations on all resources of our storage service Amazon S3. He is, however, explicitly denied access to any resources and operations of the DynamoDB service via the second statement. This now permits to define specific access control to our users. However, as you see with this example, this might not be granular enough yet. All users could access all of the data stored in S3 and DynamoDB, even content that wouldn't be theirs. So let's have a look at how we can make these access policies more specific. The following IAM policy document demonstrates a more granular use of IAM access control against the S3 and DynamoDB service. The first statement only provides access to a specific location of an S3 bucket. Here we used a Cognito identity variable, which IAM will populate with the specific user's Cognito identity. This means that a user is only allowed to operate on a subfolder in the S3 bucket which belongs to him. Operations are also restricted to only retrieve and put new objects in the user's specific folder instead of providing full access to the S3 service. The second statement defines granular access control for DynamoDB. Here we do not only limit access to a single table, but also only allow reads or writes against specific items in this table, which must start with the hash key of the specific user's Cognito identity variable. Furthermore, we only allow three attributes, username, top score, and date term, to be read from the table. And this is a powerful statement because we not only limit access to a specific table, but only allow a user to read and write only his user-specific data and not anyone else's. Fine granular access control down to an item and attribute level of an individual database table. All right, now we slowly build up the groundwork for our app. Time to test these functionalities across multiple devices and operating systems. To do this, we will leverage AWS Device Farm. This service allows you to test and improve the quality of your application on actual, real, physical devices. Amazon has racks full of actual phones and tablets from various manufacturers. And unlike emulators, physical devices give you a more accurate understanding of the way users interact with your app by taking into account factors like memory, CPU usage, location, and modifications made by the manufacturers and carriers to the firmware and software. The devices available feature a variety of different versions of the operating systems and configurations. All kinds of Android, iOS, and Fire devices are available for fully managed tests, which can even run all in parallel, allowing for excellent scale and quick and cost-efficient testing. Cost-efficient because you are only charged on a per-minute basis as the device executes your tests. Testing can be executed then in fuzz mode, where Device Farm will try to push, swipe, and click any button and area of your app. But we also allow you to run through your own testing framework, run your specific tests, and define their outcomes. We also support integration with other common testing frameworks, such as, for example, Appium or Calabash. The end result of the testing will be detailed testing reports that show exactly what test went true, where warnings occurred, and where complete failures happened. This report allows you to look into detail what went wrong. You can drill down on the individual device and model and see all the log files and performance data to decide what went wrong. We even provide screenshots and videos of the entire test. Sometimes you might also just want to experience your app or even website, since you can also use the native browser of the device on that device. Herefore, AWS Device Farm offers a so-called remote access. It allows you to gesture, swipe, and interact with the device in real time directly from your web browser. Now you have the power to not only test, but actually experience how a certain user will see your app or website on his phone. Great, so now we tested extensively what we already built. Now is also a good time to straight away think about analytics, to better understand how users will interact with our app. For this, we will leverage Amazon Mobile Analytics, which allows us to collect, visualize, and understand our mobile app usage. It's a fully managed service, so it seamlessly scales to potentially billions of incoming events from devices all around the world. But most importantly, just like with all of our other services, you always retain full control and ownership of all the data that has been collected. Amazon does not make any secondary use of your data. Now, the result of this data collection will then look like this: a dashboard that shows user activities such as daily active or monthly active users, retention stats, stickiness factor, or even lifetime values per users if you happen to offer in-app purchases. Mobile Analytics also offers you the flexibility to create your own custom events, to get insights into app-specific actions that your users take. Think, for example, about a news app, where we want to track how often an article has been shared or liked, the amount of songs that have been listened to within a music app, in-app purchase popularity, or even player abortion rates if we have a level-based mobile game. Not only will Mobile Analytics collect and store all these events and data points securely, it also visualizes them in dashboards. If, however, those dashboards do not suffice, you can also automatically have all these data points loaded up in your analytics services, such as our data warehouse, so you can run your own reports or even machine learning models. How do we initialize mobile analytics? Well, simple. One line of code where we create a new Mobile Analytics Manager instance, and that's it. We now start tracking our users and understand how they use our app. Time to build out our backend of the app. For this, we will use AWS Lambda. AWS Lambda allows you to run your code fully managed in the cloud. We will take care of all the important things like scalability, high availability, or even fault tolerance. You just put your code and let us worry about the rest. This code can then be executed via an invocation, basically an API call, straight from your mobile devices. But even better, we can also have this code executed whenever something in our cloud environment happens. If somebody uploads a new picture into our storage service, execute your code. If somebody updates or writes new data in our database, execute your code. If somebody changes his local Cognito preference file, execute your code. You get the picture. Now, the other great thing about AWS Lambda is that it automatically scales to any incoming event rate. And yet we only charge you for the execution time of your code. If your code doesn't run, then there's no charge for it. perfect for mobile apps where usage is often unpredictable. Now, how would we call such a Lambda function? Well, with the mobile SDK, it's as easy as annotating your local function on the device to tell us what Lambda function you want to call in the backend. Here I provided an example where we create a function called local function, which calls the local device code. But it also calls an AWS Lambda function called cloud function. The cloud function here only returns our backend timestamp as an example, but could include much more advanced functionalities. Invoking this function of our device with a string could give us back a result such as what you see on the bottom, where we called the backend timestamp. All done with a few lines of code, straight to a backend that scales to any amount of users, while we only get charged for the actual execution time. But how could we even build a better backend? Think about what we're trying to achieve. Our mobile app talks to some form of backend logic, which in effect reads or writes data from a database and returns it back to the mobile app. With the help of Amazon's API gateway, AWS Lambda and any database service, such as Amazon DynamoDB, we can create fully scalable and managed microservices for your app functionalities. And in alignment with the concept of service-oriented architectures, we can now build out microservices for all our app functionalities. A great way to independently develop and build out functionalities. Now, you might ask, what is Amazon API Gateway? Amazon API Gateway is a fully managed and scalable RESTful API Gateway service. It allows you to have a front door to all your APIs, which could sit in an AWS Lambda function, your virtual server, any AWS API, or even your on-premise machine. In mobile apps, latency is important, and often last-mile connectivity can be intermittent or slow. So it's essential that we have our API entry point as close as possible to the end user, so we can have low-latency API calls. API Gateway is powered via our 55 edge locations all across the world, where an end user is then automatically sent to the endpoint with the best connectivity. And talking about availability, it's also important to note that this service will provide you with a distributed denial of service, in short DDoS, attack protection. Furthermore, we can also throttle individual abusive users. Lastly, it also allows us to nicely switch between API stages and versions to facilitate API changes or developments. Now, great. Now, the next step for our app is to allow users to generate and upload their content. To store and deliver content effectively, we will leverage Amazon S3 and Amazon CloudFront. Amazon S3 is a highly available and resilient object storage, which allows you to store virtually unlimited amount of static objects such as images, videos, documents, or audio files. Amazon S3 automatically replicates your data across 3 facilities within the region of your choice and is designed for 11 nines of data durability, making it also a perfect place to store your backups. It furthermore allows to store objects in a so-called Amazon S3 bucket publicly, which provides an HTTP or HTTPS endpoint to this object, effectively making Amazon S3 an ideal place to store and serve up user-generated content without managing any servers. And to render content delivery even more effective, we will leverage Amazon CloudFront. Amazon CloudFront is a fully managed content delivery network, which will serve up your content from any of our 55 edge locations across the world. Content such as images, for example, are cached on those edge locations, and end users are sent to the edge location with the lowest latency to their device. Especially for apps with a global user base, using Amazon CloudFront in front of your app can substantially improve app performance and reduce load time for content. To use Amazon S3, we will leverage again our mobile SDK. The mobile SDK comes with connectors for AWS services, but it also contains certain helper utilities. For Amazon S3, we provide a so-called transfer utility. This utility eliminates all the additional code overhead when it comes to uploading or downloading files to S3. It will detect whenever your device is disconnected from the internet, and it will automatically buffer or retry transfers. It furthermore makes use of background compute cycles to continue up and downloads even after your app has been suspended. This makes uploading and downloading objects possible with a single line of code, as demonstrated on the current slide. After a quick initialization of the S3 transfer utility, a simple upload or download command suffices to operate on our highly available and resilient object storage. Now, talking about background activity. When your mobile app is suspended or put into the background, we can't execute code anymore. In this scenario, mobile push notifications can be used to wake up our app at any point in time and execute pieces of code. For this, we will leverage Amazon SNS Mobile Push. Amazon SNS, our simple notification service, allows to notify various endpoints such as queues, APIs, email endpoints, and also mobile apps via its mobile push notification functionality. It is a fully managed cross-platform mobile push intermediary service. As such, it allows to push out notifications to potentially millions of devices, regardless if these are iOS, Android, Windows, or Kindle devices. Amazon SNS becomes your single entry point for all your providers. It furthermore adds the capability to create topics, such as geographic or interest-based topics, to automatically fan out messages to multiple users via a single API call. Now let's have a look at our code example to see how this works. After our devices have been registered to SNS, we can use any of our SDKs to actually send out mobile push notifications. For this example, I chose our Node.js SDK and use an AWS Lambda function to send out a mobile push notification. We can now publish to an endpoint ARN. ARN stands for Amazon Resource Name, by the way. The endpoint ARN can be a topic, a multitude of devices, or, just like in this example, a single specific device. After initializing our SNS object, it's as easy as calling a send message function. SNS will now handle all the heavy lifting behind the scenes, contact the push notification gateway, fan it out to multiple devices if we publish to a topic, and buffer the message if for whatever reason the endpoint of that provider would be unavailable for a while. And voila, we sent our first mobile push notification, again with a single line of code. Let's move on to storing user data. We already allowed for static content such as images by using Amazon S3. But how about more specific user attributes or text input, which we want to make indexable and searchable? Therefore, we will use Amazon DynamoDB. Amazon DynamoDB is our fully managed NoSQL database service. NoSQL in the sense that it's a schema-less data model, so any item can have different attributes stored with it. Ideal for mobile apps where we often store different attributes per user or use case. We also don't want to put any limitations of storage or throughput. So you can store any amount of data in this database service and scale up from a few writes per second to potentially millions of read and writes per second, all whilst only being charged for your actual provisioned throughput. This scalability is completely seamless. So no matter how big your data size, write and retrieval time will always be in the single-digit millisecond range. Similar to other services, DynamoDB is also replicated across 3 facilities within the region of your choice. This makes the service highly available, but also durable. Every write to DynamoDB needs to be acknowledged in quorum before you will receive a return, making our data safe from corruption or accidental loss. How do we use DynamoDB? Well, with the Mobile SDK, we get another neat functionality with the so-called ObjectMapper. It allows us to annotate any class within our local mobile app code so that these object attributes are stored in DynamoDB. Here I chose the example of the user class, where we want to have attributes like nickname or user hash stored in the user DynamoDB table. After annotating our class, we can now start creating objects from it. To store them in DynamoDB, we only need to call the save method on the object mapper. To update a value, we update the value, such as the score here, locally in the object and call again the save method. To load up data, we can use the mapper load function. And that's it. Safely retrieving and storing data at any scale and cost effective with a few lines of code. Now, great. We're nearly done now. The last thing we want to do is provide our app the ability to record events in real time and stream them back to the cloud. Now, for this, we will use Amazon Kinesis. Amazon Kinesis is a fully managed and scalable real-time data processing service. It can scale to potentially millions of events, such as user interactions, and react upon them in real time. And that's ideal for games or interaction-based apps. It allows us to monitor users, build data models around them, such as machine learning models, and create real-time predictions or interactions with them. This stream storage is also reliable and highly available. And how do we achieve this? Well, you guessed it right. Data, again, is replicated across 3 facilities within the region of your choice. Now, how do we use Kinesis? Again, Mobile SDK provides us with a convenient utility called Kinesis Recorder. After initializing it with a few parameters, such as the region we want to use and our Cognito credential object, we can start writing events to it. Here I just wrote 2 simple test messages. After calling the submit all records method, Kinesis Recorder will stream back these information in real time for our backend to react and interact with the user. And that's it. We built our first fully scalable, highly available, reactive and cost-effective mobile app, completely without running or managing a single server. Now, let's have a look at how we could make this even easier to use. For this, we launched AWS Mobile Hub. It allows you to build, test, and monitor mobile apps within minutes. It's basically an amalgamation of all our mobile-specific AWS services into a single console. Now, it's not only a simplified user interface, it also provisions all the necessary AWS resources for you based on the features you selected for your app. Lastly, it also creates the complete code for the baseline of your mobile app for iOS or Android, all whilst respecting AWS security best practices. Now, how does that look like? After clicking on the Mobile Hub service, it will present you with a console to configure, build, test, and monitor your app, as well as a dashboard to list out provisioned resources. Let's try to configure something. Here we are presented with a simple interface to add functionalities to our app, such as user sign-in, push notifications, or cloud logic. All these functionalities are powered by the respective AWS services, which we ran through earlier. Mobile Hub will now automatically provision all those resources, such as the Cognito identity pools, S3 buckets, CloudFront distributions, or Lambda functions, all depending on what functionalities you choose for your app. And in the last and final step, it will create a complete sample application for you with all your specific functionalities directly tied to the newly created AWS resources. This can serve as baseline for your app or also as a great place to start working off of the created code snippets. And that's it. We built our mobile app on AWS. Now, let's recap what we've achieved. We built a mobile app that directly connects to the AWS cloud without any servers. All the services we have used are pay-as-you-go, meaning that we only get charged for the consumption of these services. If nobody is using our app, we don't get charged, even though we have a highly available and scalable services in the background that are ready to scale to potentially millions of users. API calls to backends are channeled to our global edge locations to provide optimal network performance. And lastly, all of the services are fault tolerant and are designed to be highly available and elastic. So AWS and mobile apps, it's a fantastic combination. And with AWS Mobile Hub, we can even get started within minutes. That's all we get for now. However, to gain more confidence and hands-on experience with AWS, you can watch our instructional videos and explore the self-paced labs, attend our instructor-led classes by qualified AWS instructors, and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. And lastly, validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. And you can get more information at aws.amazon.com/training. Now I want to thank you for attending the session. We hope you found this interesting, and please to provide us your feedback and let us know how we can improve the event experience for you in the future.